Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss sequences, sums, and series. So, in this topic we will describe both finite sequences and sums of those sequences. We will investigate arithmetic and geometric sequences, and we will determine values for arithmetic and geometric sums. We will then proceed to describe infinite sequences and their corresponding series, which is when we add an infinite sequence, and determine values for arithmetic series and geometric series. Now, a finite sequence is just a fixed number of values where each value or term in that sequence is assumed to occur after the previous term. So, for example, in engineering, you may have a finite sequence of n temperature readings. The first reading being T sub 1, then T sub 2, then T sub 3, and going on until we have n readings in total. Under certain circumstances, we may want to find the sum of such readings. So, a sum of a finite sequence is just adding these values together. Now, what we're going to introduce now is a different way of writing such a finite sum. So, here we see the capital letter, Greek letter sigma, and beneath it is k equals 1, above it is n, and then we have the term t sub k. So the Greek capital letter S, or capital sigma, is used for summation notation. So every single term in the sum is described by t sub k, whatever formula that may be. The index of summation is a variable k, and that variable k will start with the lower limit, in this case 1, and we will sum up all values with terms having the index equaling the lower sum all the way up to the upper sum. So for example, if n is equal to 5, then the index of summation will run from 1, 2, 3, 4, and 5. And so this sum would be t sub 1 plus t sub 2 plus t sub 3 plus t sub 4 plus t sub 5. So basically, a finite sum using sigma notation simply has you substitute the index of summation with every single integer starting from and including the lower limit and going up until the upper limit. Now, our lower limit in engineering is almost always going to be 0 or 1, basically the time that the system is being turned on. So for example, this sum here simply represents T1 plus T2 all the way up to adding T5. Now, more specifically actually, the term description may be a formula rather than just an arbitrary T sub k. So let's say that the term is just k. In that case, we just substitute the value of k equaling 1, 2, 3, 4, and 5 to get that this is the sum 1 plus 2 plus 3 plus 4 plus 5, which is equal to 15. On the other hand, suppose the term description was k squared. Well, in that case, you would again substitute k going from 1 to 5 into the expression k squared and add them up. This essentially gives you 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is 55. Here's a different sum. Suppose I had the sum going from k equals 0 up until 5, and the term description is 8 times 2 to the k. Well, this would be 8 times 2 to the 0, which is just 8, plus 8 times 2 to the 1, which is just 2, so that's 8 times 2 is 16, plus 8 times 2 squared, which is 8 times 4, 8 and 8 is 16, 32, and so on and so forth, all the way up until 5. And when you sum all of these values up together, you get 504. Now, very often in this course, the upper limit is just going to be an unknown positive integer n. So therefore, this sum going from k equals 1 to n simply sums the values t sub 1 all the way up to t sub n. If I was to sum k going from 1 to n, then this would just be the sum we see on the right-hand side, which of course we can't really, well, perhaps we can, determine until we actually have a fixed value of n. Alternatively, we may have the sum of the squares with the integers going from 1 to n, and so this would be 1 squared plus 2 squared plus 3 squared all the way up to n squared. Or we may have the following sum where, again, we are just substituting values of k going all the way up from 0 to n. Now, in any sequence of the form, an initial value a, then a plus d, then a plus 2d, then a plus 3d, and so on and so forth, up until a plus nd, is said to be an arithmetic sequence. So basically, every subsequent term in the sequence is d larger than the previous term in the sequence. So for example, here we have an arithmetic sequence, 3, 5, 7, 9, 11, 13, 15, going all the way, assuming the same pattern, up until 101. So in this case, a is equal to 3. The difference is 2, and n is equal to 49. And how do we find 49? Well, we just solved 3 plus 2 times n is equal to 101, in which case we find that n is equal to 49. Now, an arithmetic sum is the sum of the terms of any arithmetic sequence. So we would just sum the entries up in any arithmetic sequence starting at a and ending at a plus n times d. Now, note out of this, there are n plus 1 terms, and each of those terms has an a in it. So essentially we have a plus d plus a plus 2d, and so on and so forth. But we could actually just sum up a n plus 1 times, and so we could factor that out. So this arithmetic sum is equal to n plus 1 times a plus 0 plus d plus 2d plus 3d plus and so on and so forth. Oh, but wait a second now. Looking at that sum on the right-hand side, notice that we have a common factor of d. So now we can factor out a common factor of d. So now we're just left with this arithmetic sum equaling n plus 1 times a plus d times this sum here. And as you may recall from a previous slide, we can write that sum 0 plus 1 plus 2 plus 3 all the way up to n as the sum of k going from 0 to n. So question, what is the value of this arithmetic sum summing k going from 0 to n? Well, fortunately, Gauss, the mathematician, discovered this formula when he was 7. Now, what did he do? Well, he just wrote down the sum of the entries in order. Okay, reasonable. Now, let's write those same entries down, but let's write them down in reverse order. So now we start with the largest entry first, then the second largest, and then the third largest, and so on and so forth, up until we're adding 2 plus 1 plus 0. And then he realized, let's just add these two numbers, or let's add these two sums. But instead of just adding them as per normal, let's just first notice that 0 plus n is n. 1 plus n minus 1 is n. 2 plus n minus 2 is n. 3 plus n minus 3 is n. Oh, wait a second. N minus 3 plus 3 is n. N minus 2 plus 2 is n. N minus 1 plus 1 is n, and n plus 0 is equal to n. All right, so if we take the sum, and then we add to that sum that same sum, just in a different order, then we notice that this is just the sum of n plus 1 times. So notice that the sum plus the sum is equal to n times n plus 1. Therefore, since both of those sums are equal, one of those sums must be half of that. Therefore, the sum of k going from 0 to n, is n times n plus 1 all over 2. So, for example, the sum of the integers k going from 0 up until 100 is 100 times 101 over 2, which is 5,050. All right, straightforward enough. You'll also notice that it's divided by 2. So you may ask, is it not possible that you might get a fractional answer? And then you quickly should realize, well, wait a second. If n is even, then it's divisible by 2. And if n is odd, then n plus 1 must be divisible by 2. And so ultimately, for any value of n, this formula must result in an integral value. All right, so therefore the arithmetic sum starting at a and then proceeding to a plus d plus a plus 2d and so on and so forth up until a plus n times d can be written as this sum here. And we saw that this is equal to a times n plus 1 plus d times n plus 1 over 2. All right. And that's just this formula here rewritten. Now, you don't have to memorize this formula. Honest, you'll never need it. However, you can trivially deduce this formula from the previous formula that we saw. The sum of k going from 0 to n, is n times n plus 1 over 2. That's what you have to remember. Now let's look at some other properties of sums. Suppose we had b times a sub k being the term of the sum. Well, that's just b times a sub naught plus b times a sub 1 plus b times a sub 2 and so on and so forth. Now, in this long sum ending at b times a sub n, there's a common factor of b. So could we not factor that out? And so is this not equal to b times the sum of a sub k going from 0 to n? Yes, it is. And so therefore we have the following formula. The sum of b times a sub k going from 0 to n, when b is constant, is just b times that sum a sub k, going over the same range. Now also, if the term description is just 1, then the sum k going from 0 to n of 1 is just 1 plus 1 plus 1, a total of n plus 1 times. Well, 1 added to itself n plus 1 times is just n plus 1. Note also, of course, that if we sum from k equals 1 to n, the sum of 1 going over that range is just equal to n. We're essentially excluding the term when k is equal to 0. Similarly, if every single term in the sum is a sum of two separate terms, here I have a sub k plus b sub k, well, that is just the sum we see on the right-hand side. But can we not collect all the a terms and then all the b terms? Well, yes, we can. And is not the first sum just the sum of the a sub k's, k going from 0 to n? Yes, it is. Is not the second sum the sum of the b sub k's, k going from 0 to n? So yes, the sum of a sum of two terms is the sum of each of those terms. All right, so where might we use this? Well, suppose we had the sum k going from 0 to n of 1 plus k. Well, that's just equal to the sum of 1, k going from 0 to n, and plus the sum of k going from 0 to n, which is just going to be n plus 1 plus n times n plus 1 over 2. Now, previously we deduced that given the arithmetic sum a plus k times d, where k runs from 0 to n, that's equal to n plus 1 times a plus d times n plus 1 over 2. Can we deduce this formula just from the rules that we just saw? Well, the first thing we note is that the sum of two terms is just the sum of those terms added together. So we have the sum of a, k going from 0 to n, plus the sum of k times d, k going from 0 to n as well. Now, in the first sum, we have a common factor of a, and in the second sum, we have a common factor of d. We don't have a common factor of k because k changes with every single term in the sum, but the d does not. So therefore, we can factor out an a from the first term and we can factor out a d from the second term. Now, the sum of 1, k going from 0 to n, is just n plus 1. The sum of k going from 0 to n, is just n times n plus 1 all over 2. So if we substitute these two formulas back in, we get the formula we deduced previously. So we got the same formula, except we're now using the properties of sums to get that formula. Next, we're going to look at geometric sequences. Now, a finite geometric sequence is any sequence that starts with a value a, which can be arbitrary, and then each subsequent term is the previous term multiplied by a common ratio r. So a times r is just ar times r is ar squared times r is ar cubed, and so on and so forth. So any sequence that satisfies this is said to be a geometric sequence. A geometric sum is the sum of such a sequence. So it's a plus a times r plus a times r squared plus a times r cubed plus so on and so forth up until we get to a times r to the n. Well, we can write this sum using summation notation. We are summing a times r to the k, where k runs from 0 up until and including n. Now, the first thing we note with any geometric sum is that there's a common factor of a. So this geometric sum can simply be written as a times the sum of r to the k, where k goes from 0 to n. Thus, what is this finite sum of r to the k, where k runs from 0 to n? Now, to determine what this sum is, let us do what we did in secondary school. We'd multiply it by 1. All right, how does that help us? Well, it helps us if 1 happens to be 1 minus r over 1 minus r. All right, so previously we saw that if we have a sum where each term is multiplied by a scalar, then that scalar can be taken out. However, therefore, if we have a sum where the sum is multiplied by a scalar, say 1 minus r, then that's the same as if we had the sum where each term was multiplied by that same scalar, specifically 1 minus r. So these two sums are equal. All right. Now, inside the sum, we have 1 minus r times r to the k. Well, I can just expand that out to get this difference, and that difference is just r to the k minus r to the k plus 1. Now, you may recall, however, that the sum of two terms is just the sum of the first term plus the sum of the second term. Well, in the same way, you may be able to deduce that the sum of a difference of terms is simply the difference of the sums of those terms. All right, that's straightforward enough. So now we need to calculate the formula in the top right-hand corner. But to calculate that formula, we have to know what this difference of sums is. Well, if we write out the first sum, we get 1 plus r squared plus r cubed plus all the way up to plus r to the n. From that, we subtract the sum r plus r squared plus r cubed plus all the way up to plus r to the n plus 1. You'll notice that we have r minus r, which cancel each other out. We also have r squared minus r squared, which cancels each other out. These terms cancel each other out, as do these, and finally r to the n minus r to the n is 0. The only terms left now are 1 and minus r to the n plus 1. So this difference of sums is just 1 minus r to the n plus 1. So we can substitute that into the formula to get this formula here, which can be rewritten in the format you saw in secondary school: 1 minus r to the n plus 1 all over 1 minus r. Now, we've previously discussed finite sequences. Now we're going to discuss infinite sequences. So the first is just an arbitrary infinite sequence which goes on and on forever. The second is an infinite arithmetic sequence, and the third is an infinite geometric sequence. These are actually very useful for engineers. Why? Because when you turn a system on and you have a sensor that is reading some value periodically, you actually never usually know a priori when that system may actually be turned off. Now, in analyzing such systems, you may actually want to calculate the sum of an infinite sequence. And a series is a sum of an infinite sequence. Sometimes you hear the term finite series, but we're going to use the word series to describe an infinite sum of an infinite sequence. So for the three infinite sequences we see above, we have corresponding series. Now, an arithmetic series is boring. In this formula, if d is greater than 0, no matter what happens, the sum is going to be infinity. So 1 plus 2 plus 3 plus 4 plus 5 and so on and so forth is ultimately going to equal infinity. Even if a was negative a million, you're going to have negative million plus negative 999,999 plus negative so on and so forth. But sooner or later, as you keep on adding, ultimately you're going to go back up to infinity. It's also true if d is equal to 0 and a is a positive value. This infinite sum or series is 0 only if d is 0 and a is 0, and if d is negative or d is 0 and a is negative, then this infinite series is negative infinity. Not very interesting. Now, what do we do about a geometric series? Well, recall that this is the formula for a finite geometric series. However, notice also that if the absolute value of r is less than 1, then as n becomes larger and larger, r to the n plus 1 gets closer and closer to 0. So for example, if r is equal to 1/2, r to the 1 million is half that of r to the 999,999. And r to the 1,000,001 is half of the previous value. So as n becomes larger, r to the n plus 1 gets smaller and smaller until it becomes insignificantly small. Consequently, we can imagine, although this is bad mathematics, that this infinite sum is just 1 minus r to the infinity plus 1 over 1 minus r, and if the absolute value of r is less than 1, we can cancel that term out, so that's just left with 1 over 1 minus r. Okay, that seems reasonable. And in your calculus course, you will learn about limits, so you will be able to deal with this more analytically rather than hand-waving as we've done here. So, for example, 1 plus a half plus a quarter plus an eighth plus a 16th and so on and so forth, going on to infinity, is just this infinite geometric sum where the ratio is 1/2. Oh, but wait a second. That's therefore equal to 1 over 1 minus 1/2. So therefore it's 1 over 1/2, which is equal to 2. All right, is that reasonable? Well, 1 plus a half is 1 1/2. 1 plus a half plus a quarter is 1 3/4. 1 plus a half plus a quarter plus an eighth is 1 7/8, and so on and so forth, getting ever closer to 2. So yeah, that's reasonable. Now, what happens if we have a common ratio of 1/3. So that's equal to, so that is the infinite series 1 plus a third plus a ninth plus a 27th plus 1 over 81 and so on and so forth. Now, each of these terms is smaller than the previous infinite sum or series, and so we expect this answer to be slightly smaller. And calculating it, we get 1 over 1 minus a third, which is equal to 1 over 2/3, which is 3 over 2, or 1.5. Similarly, you can have a common ratio that is negative, but still less than 1 in absolute value, such as -1/2. So we have 1 minus a half plus a quarter minus an eighth plus a 16th, and so on and so forth. Well, that's just 1 over 1 minus the common ratio, which is -1/2, so that's 1 over 1 plus a half, which is 1 over 3/2, which is 2/3. Okay, that's smaller than either of the previous two sums. And here we have the common ratio being -1/3, so that is 1 over 1 minus -1/3, which is 1 over 4/3, which is 3/4. So what you have to remember from this talk are the following concepts. The sum of k going from 0 to n is just n times n plus 1 all over 2. The sum of r to the k going from 0 to n is just the ratio you learned from secondary school, 1 minus r to the n plus 1 over 1 minus r. And if the absolute value of r is less than 1, then the infinite geometric series equals 1 over 1 minus r. You'll also have to remember that the sum of 1 going from k equals 0 to n is just n plus 1. We can factor out a common term of b if every single term is multiplied by b, and if we have the sum of two common terms, that is equal to the sum of the first term plus the sum of the second term. Consequently, in this topic, we've introduced sequences, sums, and series. A finite sequence is a fixed number of values in a given order. A sum of a finite sequence is just the sum of those terms. We described arithmetic and geometric sequences, and we found the sums of these two sequences. We also found formulas for infinite geometric sums, also known as geometric series. Sometimes, on occasion, a finite sum is also called a finite series. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!